Hello everyone, welcome to another episode of my YouTube channel Data Science with Sam. This vlog is a continuation of the computer vision series that I started a week back. In my previous vlog, I gave you a brief overview of what is computer vision, how this field of technology revolutionized artificial intelligence. I also give you a kind of few examples of very widely popular computer vision applications in different industries such as healthcare, retail, or even movie industry. So now, in today's blog, I'll talk about object detection. But before I proceed further, please don't forget to like and subscribe to my channel because more contents on data science, machine learning, and computer vision are forthcoming. Now, what is object detection? Object detection is a collection of computer vision tasks that cater towards identification of semantic objects in a digital photograph or video. For example, if you see an autonomous car or any like a surveillance system, you must be wondering that how they will usually detect the presence of an object, whether it's a human being or any other cars or trees or any other objects in a running video. So usually what happens that those especially the autonomous car, use this object detection technology and detect everything in runtime. So when the car is moving, it's basically detecting all the objects runtime and finding its way through and avoiding all obstacles. So now let's check out in the next section that how this object detection technology is derived into two different mechanisms. The idea of object detection technology is mainly built on two different mechanisms. One is object localization, another one is image classification. Object localization helps computer to determine the location of the object. It provides an image with one or more objects as an input, and then it generates output of one or more bounding boxes that indicate the accurate location of that object in a static image or in running video. After locating the object, then computer tries to determine the class of that object. In that case, it usually passes an image with a single object as an input, and then it generates the class level or the probability score as an output just to determine that object belongs to a certain class. For example, in this picture, computer determines the location of that blue sedan by using object localization technique, followed by the image classification technique, which determined that blue sedan, the blue object, belongs to a car class. You must be wondering what is the 0.79 value means. So that means the computer was able to predict 0.79 score of this blue object classified as a car. Similarly, for the traffic lights signal, the computer was able to determine that this particular object belongs to a traffic light class, as it shows, it gives a 0.61 probability score. So now let's check on in the next section how YOLO model architecture plays a crucial role to classify an object in conjunction with locating that object accurately in a static image or video. YOLO model is a state-of-the-art model to achieve higher accuracy in performing object detection of a static image or a running video in real time. The acronym YOLO stands for You Only Look Once. That means the model will perform one forward propagation to process an image and make predictions accordingly. It is usually comprised of a single neural network which takes an image as an output, and then it will pass it to like different convolutional and nonlinear layers and predict the probability of the bounding boxes to accurately define the location and the classification of an object. This particular model was first introduced back in 2012 in one of the ImageNet classification competition. This model architecture was inspired by GoogleNet. So the model network is comprised of 24 convolutional layers and 2 linear layers. Like for example, if you see this picture here, you could see we have 24 convolutional layers, like 1, 2, 3, 4, 5, 6, 7, 8. And here you actually 2 convolutional layers are being repeated for 4 times. So there'll be like 4 multiplied by 2, it's 8. So 8 and 8, 16. Here also the convolutional layers, 2 convolutional layers are repeating for 2 times. So it'll be 2 by 2, 4. So 16 plus 4, 20. And then
then 1, 2, 3, 4. So there are like total 24 convolutional layers are being resided in this model architecture. And in between, we have 1, 2, 3, 4 max pool layers just to reduce the dimension of the image. So originally, when this model architecture was introduced, it used to take an image of dimension 448 by 448. But when they, when they pre-trained the model with the image data set, they reduced the dimension to our standard size 224 by 224. Now, it also has two connected linear layers before it provides the output in a form of like a probability class of the bounding box. Now, if you're wondering that, okay, so you just mentioned that based on the YOLO model architecture, it takes an image as an output and provide the probability as a form of bounding box. Could you please tell me more about the bounding box? So let's move to the next slide for that. So let's take an example of this particular image on the left. So here the processed image actually has a dimension of 608, 608. It has like 3 layers. So that's why the 3D dimension is 608, 608 by 3. So you pass this image to YOLO model. So what YOLO model is doing is that it's trying to create the bounding boxes. It created a 19 by 19 grids, and the output is basically the list of those bounding boxes, which are actually resided in these 19 by 19 squares. So each of these small boxes pointing to are actually combination of different bounding boxes. Now you must be wondering how the bounding boxes looks like. So the bounding boxes are actually represented by 6 numbers. One is the 6 numbers are like, first is the BX, BY, BH, BW. So BX, BY is representing the location of the bounding boxes based on X and Y axis. Then we have this BH and BW, which is nothing but kind of like the actual height and width of the bounding box. In general, for this example, that BH, BW parameter is 5. Now, the next thing is the C. So C actually represent the class. So for each bounding boxes, we need to predict the class and their corresponding probability factor. So in that case, PC and C is those two parameters are very important, because those two parameters will denote that that particular bounding box belongs to which particular object. Okay, so now once we gather these 6 numbers from each bounding box of this 19 by 19 grid, then we'll pass it to the next stage for probability extraction to determine the accurate class of the object. So in a nutshell, the architecture for this my model was actually we are passing the image of 608, 608 and 3 dimension. So the M denotes the the number of images we have, and once we pass this image through an YOLO model network, then the model actually encoded that the image in the form of a list of bounding boxes and provides output in this format. So here the 85 is basically denoting the number of bounding anchor boxes plus the number of classes. So here we have 80 different classes for this prediction purpose. So the actual number is 85. Now, the next thing is, so once we generate the output from each bounding box, how are we calculating the probability? So for that, as I mentioned that for this particular example, we have 80 different classes. So that means we already trained the model with 80 different objects. Like there's one object, maybe car, there's another was traffic signal, there's another object, maybe tree. So our model, our computer vision model, this YOLO model, understand that how a car looks like and how it will be distinguishable from a human being or a traffic light. So once we get all the probability measure from each bounding box, then our YOLO model will try to determine the accurate class. So in that case, it gets that PC, the probability measure from each bounding box, and it performs an element-wise product with the list of different classes. So after it performs the element-wise product for each class, the computer would provide an output of the final probability score. Like for C1 class, the probability score is 0.12, for C2 0.13, for C3 0.44. So now, finally, it will actually pick the maximum prediction score and then classify the object based on that final, the maximum probability score. Like for here, so like that bounding box determined that object as car based on the probability score 0.44, which denotes that the object belongs to the class 3. So in a nutshell, the scores actually represents the probability of an object belongs to a certain class.
So this brings me to an end of this vlog on object detection, and also it gives you a brief overview of how you can apply YOLO model to perform the object detection exercise for your data science or any artificial intelligence related work. Now you got an idea about how this YOLO model architecture looks like. Now you know that how you can apply that YOLO model network to transform an input image in such a way that it will be able to identify the object, the local area, the position of the object. It can also be able to identify the class of that object. Now you must be wondering that, okay, so I got a theoretical idea of this object localization and image classification, but now how I can implement that YOLO model in code. So in my next vlog, I'll give you a code walkthrough of how we can apply YOLO model using Python. So stay tuned for that. And also I would recommend you to check the video caption section where I share some of the materials related to the YOLO model and object detection technology. So please read those materials, and that will give you an additional knowledge about this intriguing computer vision technology. So that's all for now. I hope you are enjoying the holiday season and wish you a Merry Christmas and Happy New Year ahead of the time. So till then, goodbye.